All right, now we're going to talk about the idea of an electric current. And the story about current starts with the idea of charge. So we've learned that we have two kinds of charges, positive and negative charge. We'll just make up two little charges like that. And we know if they're the opposite sign, that there will be a force of attraction between them. And if they have two like signs, here's two charges that are both positive, and these charges are going to repel each other. So this is the basic electrostatics idea. And the same thing for two minus charges, they also repel. So like charges repel and unlike charges attract. That's one idea. So we have the idea of charge. And now we need a place to get some charge. And one of the places we like to get charge from is copper wires. A copper atom looks like this. A copper atom has a nucleus with some protons in it, and it also has electrons flying around the outside, electrons in orbits around the outside. So we'll draw the electrons like this. So there'll be orbits around this nucleus. Pretty good circles. And there'll be electrons in these. Little minus signs. There's electrons stacked up in this. And even farther out, there's electrons. So there's a kind of a interesting looking copper atom. Copper, the symbol for copper is Cu, and its atomic number is 29. 29. That means there's 29 protons inside here, and there's 29 electrons outside. And it turns out, just as a coincidence for copper, that the last orbital out here has just one electron in it. That guy right there. And that's the one that is the easiest to pull away from copper and have it go participate in conduction, in electric current. So when if I have a chunk of copper, every copper atom will have the opportunity to contribute this one lonely electron out here. If we look at another element, like for instance silver has this same kind of a electron configuration where there's just one out here, and that's why silver and copper are such good conductors. All right, so now we're going to let's build a copper wire. Here's sort of a copper wire. It's just made of solid copper. It's all full of copper atoms. And I'm going to put a voltage across this. There's our little battery. This is the minus sign. This is the plus side. And we'll hook up a battery to this. And what's going on in here? Inside this copper is a whole bunch of electrons that are associated with atoms. It's a neutral piece of metal. There's the same number of protons as there is electrons. But these electrons are a little bit loose. So if I put a plus over here, that's this situation right here where a plus is attracting a minus. And so an electron is going to sort of wander over this way and go like that. And that's going to leave sort of a net positive charge in this region. And so these electrons are all going to start moving in this direction. And then at the end, here, an electron is going to come out of this battery, travel in here, and it's going to go in there and make up the difference. So if I had a net positive charge here from the electrons leaving and going to the left, this battery would fill those in. And I'm going to get a net movement of charge, of negative charge, around in this direction like this. The question is, well, how do I measure that? How do I measure or give a number to that amount of stuff that's going on? So we want to quantify that. We want to assign a number to the amount of current happening here. So what we do is in our heads, we put a boundary across here. So just make that up in your head. And it cuts all the way through the copper. And what we know, we're going to stand right here. And we're going to keep our eye right on this boundary down in here. And as we watch, what we're going to do is we're going to count the number of electrons that move by here. And we're going to have a stopwatch, and we're going to time that. And so we're going to get, basically, this is charge. It's negative charge, and it's moving to the side. And what we're going to do is at one little spot right here, we're just going to count the number that go by in 1 second. And so we're going to get charge per second. And it's going to be a negative charge moving by. And that's what we call current. And it's the same as water flowing by in a river. That's the same idea. All right, now I'm going to set up a different situation that also produces a current. And this time we're going to do it with water and salt. So here's just, let's build a tube of salt water like this. So we're going to pretend this is some tube that's all full of water. I'm also going to put a battery here. Let's put another battery. And we'll stick the wire into there, and we'll stick the wire into there. And this is the plus side of the battery, and this is the minus side of the battery. So water is H2O, and this does not conduct. There's no free electrons available here. But what I'm going to do is I'm going to put some table salt in it. This is ordinary salt that you put on your food, and it's made of sodium. That's the symbol for sodium, and chloride. Cl is chloride. Sodium chloride is table salt. If we sprinkle some table salt into water, what happens is these dissolve, and we get a net plus charge here and a net minus charge on the chlorine. So out here is floating around NAs with plus signs and Cls nearby, really close nearby, with minuses. Let's keep it even, all right? Now, when I dip my battery wires into this water, what's going to happen is this plus charge over here from the battery is going to attract the minus Cls. So the Cl is going to move that way a little bit. And over here, the same thing is happening. There's a minus sign here. There's a minus from the battery. And that's going to attract this. And it's also going to repel the Cl minuses. And so what we get is a net motion of positive charge plus Q going this way. And we get minus Q going this way. And how do we measure that current? How do we measure that current? Well, we do it the same way as we did up there with copper. We put a boundary through here in our heads. We stand here, and we watch the charges moving by. And what we're going to get is some sodiums, NAs, moving this way, and chlorines moving this way, just like we showed here. Na moving this way. And so there's going to be plus charges moving through the boundary and minus charges moving through the boundary in the opposite direction. And if I take the total sum of that, for example, if I see one Na go this way and one Cl go this way, that's equivalent to two charges moving through the boundary. Hope that makes sense. It's equivalent to two charges, one going this way and one going this way. And because they have opposite signs, they add together and make two charges. In this case, current is equal, again, to charge per second.